Okay, we are continuing with the quantum software. I think Nathan already pointed OpenQAOA, a Python library. Vishal will present it. So Vishal, the stage is yours. Thank you.
Perfect. Thank you, Abu. And thanks for organizing this great conference. I already see like 170 plus participants, which is like really nice to see. And it also gives us a platform to share something we've been working on. So yeah, thanks a lot for the invitation. Okay, I hope you all can see the screen and I'm visible as well as audible as well. If not, then please feel free to let me know.
All is fine, Vishal.
Perfect. Okay, so then I can get started. So I have roughly about 25 minutes, I believe, for this presentation. So I'll take the first about, let's say, 20 minutes to quickly walk through and present what I'm here for, and then we can reserve the last 5 minutes for questions, or if you have comments or something like you guys would like to discuss. All right, so as you guys can see on the screen, I'm here to present something we've been building at Entropica Labs for the past few months. And this is essentially, the name of the software is called OpenQAOA. And as the name suggests, it's open because we plan to go open source with it in the next few months. And at the moment, it supports QAOA and its variations. Right? So before I start further and like start defining and start elaborating on what this thing is about, maybe I can give you a quick introduction about myself. So I'm Vishal. I have a bachelor's degree in engineering physics from the Indian Institute of Delhi. And then I went on to pursue a master's in physics with a specialization in quantum physics from the University of Munich, LMU, in Germany. And then I basically started working with Entropica as an intern, I think in 2020, yeah. And I essentially was working on my master thesis at that time. So my master thesis was about pulse level tools, like instead of using gates on quantum computers, like in quantum circuits like we normally do, which are essentially just definitions of microwave pulses. Some of these pulses you also saw in Nathan's talk before this. So my thesis was about the direct use of these pulses to see if we can get some improvements in QAOA. And after graduating in April, I started working full-time at Entropica, and I basically divide my time at Entropica between some research using QAOA and its variations and applying them to problems, and some other time basically building softwares like the one that you see here. All right, so that's a bit about myself, and then we can basically quickly get into the presentation now. All right, so let's start with the question. Actually, before I start with the first question, I would like to quickly say that I plan to divide this presentation mainly trying to answer 3 questions here. So the first of that question would be, what is actually OpenQAOA? So I'll quickly try to define what this thing is. The second question is I'll address is, why did we feel the need to have something like this at Entropica, and why do we think this could be a really useful or utilitarian library for people outside Entropica as well. And then the final thing I would like to talk about are basically the goals of OpenQAOA, the things that we aim to achieve using this library. And then I'll basically conclude the presentation and let you guys a chance to ask questions and have some comments. All right, so let's start with the first question. What is OpenQAOA? So if I have to define the package in one sentence, I would say that it's a Python library for optimization with QAOA. But QAOA, of course, as defined in the original paper by Edward Furry in the beginning, like in 2014, was basically a vanilla version of QAOA. And ever since then, research has progressed, and we've all seen lots of different variations of QAOA ever since, right? And essentially, it's a library for optimization using this algorithm and its variations on quantum computers and also on simulators, right? You can see I've written just quantum computers because our plan is to go and implement or like be able to execute these optimization problems on different kinds of hardwares that are available today. All right, so that's a bit of an introduction about the package itself. So since I want this talk to be as accessible as possible to a wide variety of audiences, so I mean, if you've just started your journey in quantum computing versus if you've if you're like a really distinguished researcher in QAOA, I would like to bring everyone together. And for that, maybe I'll just start with a quick introduction of what QAOA is. I won't go into too much detail here, but I'll just give you like one of the few pointers or like important aspects of the algorithm, right? So the first thing that I like to start with is it's a quantum algorithm. So there's naturally so it's a variational quantum algorithm. So there's naturally a quantum circuit that's involved here, which have these variational parameters that you can see on the screen called gammas and betas, right? So essentially, the most vanilla or the standard form of QAOA basically says that you start in this superposition state that you create using Hadamard gates. And then you sequentially and alternatively basically apply this application of these gates. So the 2 qubit gates that you can see here, which encode the problem that you're trying to solve. And then you also apply basically a set of mixer gates. So the ones that you see here, the Rx gates, the rotations around the x-axis. So these basically help you explore the solution space of your problem that you're trying to explore, right? And then essentially this is like an alternative application of these gates, and you repeat them for P layers, right? And P in literature is basically described as the depth of this variational algorithm. So I'd like you to remember this picture as we go forward, so that once we start talking about the features of OpenQAOA, you can basically quickly try and relate what exactly I'm talking about. So the main points that I'd like you to remember are that these gates are variational, so they have parameters associated with them that you can tune. And essentially the most common parameters are called gammas and betas, right? Okay, so once you have the circuit ready, this is like the quantum part of the algorithm, right? But we know like variational algorithms work on this principle of this quantum classical hybrid loop, right? So essentially, it's just a very fancy word of saying that you run a quantum circuit on a hardware. It could be a quantum computer or a simulator, and then you try to measure some quantities. Could be an observable, could be something else, and then you basically take that observable and you plug that value into a classical optimizer that works along with that with your quantum circuit, right? And the job of classical optimizer essentially is to take that quantity that you came up with and use it like an objective function and try to basically suggest new parameters that essentially minimize or maximize whatever you've designed your algorithm to be, minimize or maximize the value, and come up with new parameters that you feed back into the quantum circuit, right? So in picture, as you can see on the screen, it looks like this sort of like a feedback loop that you create this, compute this quantity from a quantum circuit, you feed it to the classical optimizer. Classical optimizer gives you updated parameters, and you run the circuit again, and you keep doing this again and again until some stopping criteria, for example, that you've defined, or the classical optimizer says, okay, this is, I've optimized this thing enough, and it's basically reached convergence, and then it spits out these optimized parameters, right? So then the point of this algorithm is basically using these optimized parameters. When you run that quantum circuit, it basically generates a probabilistic solution for you, right? So QAOA won't tell you that, okay, you've run this problem and this is the solution for you. What instead it does is it basically produces a probability distribution over the entire solution space that you have, and essentially tells you how confident or like how probable this particular state that you have as a solution is actually likely of being a solution, right? So normally we use this thing called expectation value, like this observable that you calculate with respect to the output of your quantum circuit. And this value is actually computed with respect to the problem that you're trying to solve. So one thing that I've haven't talked about here is that the optimization the optimization problem that QAOA can solve are basically these so-called quadratic binary problems. So quadratic means that they're at most 2 degree in their formulation, and binary means that the variables can take either value of 0 or 1, right? And you take these problems and essentially you map them in this object called an Hamiltonian, right? So if you're a physicist or you have some little bit of experience in physics, you know what Hamiltonians are. But if not, it's basically just an object that encodes the, let's say, the quality of the solutions that you're trying to find, right? So for example, if it's an optimization problem, you're either trying to solve the problem to find either the minimum value or the maximum value for different configurations that your variables can take. And the Hamiltonian object basically encodes the different energies or different values corresponding to each of those states. All right, so before I proceed further and let's start talking about the project itself, or like OpenQAOA itself, I'd quickly like you to meet the team behind the project. So these are the people who've been spending the last few months trying to build this project, and we've reached the state that we are at the moment, thanks to everyone that you see in the picture. So all of us combined are, everyone that you see in the slide are basically all physicists with varying levels of degrees that we have. So we have a bunch of bachelor graduates, we have postgraduates, we have PhDs, and everyone. And it's actually a really lovely team. So all of us combined, we basically have a little bit of experience running variational algorithms in general. Most of us have a lot of experience running QAOA on simulators, on hardwares, under different variations and so on. And something that all of us tend to agree on is how troublesome sometimes building this entire architecture could be, right? So for example, if I were to give you a analogy, let's say, not sure if this analogy is going to work 100%, but for example, let's say you talk about neural networks, right? You're in a university degree, you're trying to learn what neural networks are. So you start from scratch, you build your neural network in Python, you start building your neurons, you start building your layers, you start defining an activation function, and then you put everything together and you pair it with an optimizer and you try to learn and optimize these things. It's a really important process, but if you have to repeat this thing again and again for every time you have to run a neural network, it's soon becomes tiring, right? So the idea is to promote research. For example, the ideas behind softwares like TensorFlow and Keras were basically to promote research, but just like get rid of the, let's say, let's say the part that's like rut work, basically, right? So get rid of that part as well. So we kind of have approached the software from the same perspective. So if you're trying to run a variational algorithms, you have lots of different things that you have to care about when you're running these algorithms, as we'll see in the few slides that are about to come. And the idea behind that is that if you want to do that, repeat these steps again and again, soon it becomes cumbersome, right? And the process of automating is basically to get rid of that stuff and actually focus on what QAOA can do, on what kind of problems and what the results look like. All right, so before I start talking about those things, I'd quickly like to mention, so at Entropica Labs, we focus on optimization problems. Right? So there can be the two different kinds of optimization problems at the moment we focus on are the regular one that you see on the left, which is taking an optimization problem, let's say maximum cut or vertex cover or something, and encoding them into a form that can be optimized on a quantum computer, right? And then the other part is actually another interesting aspect, which is trying to optimize quantum resources that you need to be able to run these algorithms, right? So for example, we all know that one of the limiting factors and one of the major contributions to noises on quantum computers these days is basically the error rates on 2-qubit gates, right? So 1-qubit gates are really advanced, right? They have like really low levels of error rates on them, but the 2-qubit gates usually are the ones that that basically end up becoming the source of major errors on your quantum computation. So in that case, it becomes kind of important that if you're trying to run an algorithm, you go from the logical state, logical implementation of the algorithm to the physical. during that transition, there's some sort of an optimization you can do, right? Because you have some problem that you want to solve, logical problem, and you map it to a quantum computer, which is not fully connected, let's say. Only some of the qubits are connected to some of the other qubits, and it's not fully connected. So you basically have to map that problem on the quantum computer. So it's a non-trivial problem, and it's also an optimization problem. So there's another interesting aspect that we focus on at Entropica Labs. But for the purposes of this talk for today, I'll actually focus on the left-hand side, which is essentially solving optimization problems using quantum computers, right? And that's where QAOA comes in. All right, so if you guys have some experience running variation algorithms, you know that it requires you to build a whole sort of architecture around it that you need to do before you are able to run some analysis on it, right? So it's a ton of different things. Some of them I've listed here. It's not a complete list. It's not an exhaustive list, but these are some of the things that you need to take care of, right? You need to write the circuit ansatz in the hardware provider language. So this could be different if you're trying to communicate with the IBM devices. It's different if you're trying to run something on the Rigetti chip. It's different if you're trying to access the Rigetti chip using AWS system, which have their own language called Bracket. And in all fairness, these languages are really amazing, and like the ease of use is really great, and something these teams have really worked hard on. But the problem is that if I'm trying to run QAOA and I want to compare, I write the circuit, let's say in Qiskit, and I want to now compare it to the Rigetti QPUs, I need to rewrite the circuit again in PyQuil language, right? In Rigetti's language. So that's one aspect. There's another aspect that you have to take care of is basically the parameters that we talked about in the beginning, the betas and gammas, right? You have to be careful that you have to be careful that you apply all the parameters to the correct gates. The sign conventions are followed correctly. And if you were to change the parameterization, you have to repeat the step again. There are more specific things like QPU connection breakoffs. So I was talking about the quantum classical hybrid loop in the beginning, right? So you're sitting on your laptop, you're sent something, some instructions to IBM servers to run something on the machine, and then you get an answer back and you run it with your classical optimizer, and this loop repeats, right, for some number of iterations. What if the connection was supposed to break in the middle, right? Of course, there's something you can write. You can maybe write some piece of code that checks these connections and kind of handles the breakoffs quite fairly well. But again, this is like a cumbersome task that you need to do. And as a researcher, if you want to focus on what your QAOA can do, or like how you can apply it to your problem and what variations you can try, this is something that you can leave to automation, right? So these are some of the areas that we wanted to tackle when we were building OpenQAOA internally as well. Okay, so the next question that we can answer quickly is, where does OpenQAOA fit in the in this entire scheme of things, right? So you are this user who's sitting on your laptop and you're trying to run some quantum computations on either like cloud hardwares that are provided by IBM or Rigetti, or you simply just running on your local simulators, right? So OpenQAOA sits exactly in the middle, right? As a user, you want to minimize the efforts that you need to do to run a new problem with different variations on QAOA on different hardwares, right? So you say, okay, this is the problem I want to solve. You feed it into OpenQAOA, and then it basically takes care of the rest. So you basically provide some customizability in form of easy, let's say, strings or something, and OpenQAOA basically takes care of everything. It constructs the right objects for you. It handles the connections. It handles the quantum classical optimization loop and so on. And then essentially it passes down to the correct hardwares that you actually want to run your problem on. So for example, we also offer like a couple of really nice Entropica simulators. So one of them is like really fast in comparison to, let's say, IBM Q simulators or something for small problems. So it's good for prototyping, and it runs on your laptop. So there's no connection problem. So there's access to IBM Q devices, PyQuil devices, and all the exact creation of the circuit in the way that you want. the running of the optimization loop, all of this is taken care of automatically by OpenQAOA. And you as a user is basically agnostic to what you're, to the hardware you're actually running your problem on. All right, so with that, let me give you a quick overview of the features of OpenQAOA. So of course, we support a lot of different kinds of features that we think are useful from our experience with research in OpenQAOA. And this is like one of the more verbose information heavy slides of my presentation, so bear with me. But I'll quickly go through them without overloading information. So essentially, some of the features that we support at the moment are different circuit parameterization. So you can choose from the regular standard gamma beta parameterization versus Fourier, extended, and so on. You have different choices of mixers. So you can specify an X mixer, an XY mixer. You can choose different optimizers to work with to optimize your objective function. There's some slight ansatz modification. So you can basically start with some warm starting state. You can specify a circuit in the beginning of your QAOA routine. We have workflows that are built on top of OpenQAOA. So OpenQAOA is kind of like this modular Lego-like structure, and you can build like more complicated workflows on top of it. So if you don't know what QAOA is, basically a recursive form of QAOA, where you basically run the algorithm n number of times, and at each step you basically keep eliminating some number of qubits from your routine. Right? So it basically allows like easy building of these workflows on top. And since I said, like already described, that this is a modular design, so that means we can easily just add more backends, more optimizers, more parameterizations in future quite easily. So for example, if tomorrow some XYZ a cool quantum computer comes on the market, we can just easily add them as one of the backends on OpenQAOA. And as I already said, there's easy backend switching. So going from IBM Q to Rigetti is literally just one line of code that you have to change. All right, so quickly, I'll go, since I'm also running low on time, quickly go through the goals of OpenQAOA. So this also maybe has a bit of an overlap to one of the slides that I presented earlier, where I was talking about why did we feel the need to have OpenQAOA. So this is something that was motivated internally for us in the beginning, and then we think this is like also useful for the rest of the people who are using QAOA on a regular basis, right? So there's experimental reproducibility. So for example, if you have an intern who did some really great work using QAOA, and they have like tons of notebooks and scripts lying around at the corner of some machine, then we need to go through those codes. We need to make sure that, okay, this is the convention that they used. They're using beta instead of minus beta and so on. So it just makes sense that if you have some set parameters, this is the warm starting state I've used, this is the parameterization I've used, this is the initialization I've used. Basically, there's some sort of experimental reproducibility, right? That if you take those same configurations again and repeat them, you don't get a different result. There's code optimization. So basically to minimize repetitions and like bad design or things that basically make it difficult for other people to just quickly onboard with something you're doing and try to take over some of the work that you're doing or contribute to the work. There's the aspect of reducing bug rate. So this is something we've roughly also talked about, that if two different people are working on their own implementations of QAOA, there are chances that you can have bugs. Standardized implementation. So there's this thing in QAOA where the original paper was supposedly presented the QAOA problem as a maximization problem because they encode the objective function a bit differently, and some people like to solve it as a minimization problem where they encode the Z observables directly in the Hamiltonian, right? So if there's a standardized implementation of QAOA that basically is consistent throughout, then it also helps with research, right? And then finally, the last point is to improve research outputs, basically to drive away your time from constructing circuits, from managing the interaction between different objects, between optimizers, to take all of that away and actually utilize that time on coming up with better versions of the ansatz and trying different things and actually focusing on research. So this is actually like a small snippet of the code, and just to describe, just to demonstrate how simple things can be if you try to run QAOA, for example. So it's literally you assuming that you have this thing, the problem. So you already know what you want to solve using QAOA, you've defined. The 4 steps that you literally have to follow are, you create the device. So you basically tell OpenQAOA on what kind of device you want to solve this problem. And this is, I'm sorry. Oops. Can I mute? Okay, perfect. Thank you. So you just tell OpenQAOA what device you want to run this problem on. So it could be a local simulator on your machine, or it could be, let's say, on the cloud somewhere. So for example, if it's a cloud machine, then you pass your credentials, right? So for example, if you're accessing IBM devices, you have these things called API tokens and groups and whatnot. So you basically pass that as a dictionary and it creates that device for you. Then the rest of the steps are really simple. You create this model called QAOA, and then step by step, you associate the construction of this algorithm, right? You start with how many layers you want, what kind of parameterization you want, what kind of initialization you want, so on. And then you set your backend properties. If you want to use a noise model with the simulator, the number of shots you want to use, so on. And then finally, you set your classical optimizer, right? So what kind of optimizer do you want to use to update the expectation values? The final step basically just involves compiling the problem by compiling the model by passing the problem that you want to solve and just clicking something as simple as optimize. So this basically runs this loop. So as soon as you click the optimize, and let's talk about the most complicated case here where you're actually running something on the cloud device, which after each iteration has to go and talk to the QPU on the cloud. All of this is taken care of by this optimize function, right? So your circuit is sent to the IBM servers. It runs the circuit, generates some measurement results, comes back, you compute the expectation value, you send it to the optimizer. Optimizer suggests new parameters, and then it goes back, constructs another circuit, sends it to the cloud, and so on. Just keeps repeating, right? And then finally, you can retrieve this really massive object called results information, which gives you a whole lot of different information on how your optimization process went, how did your cost function look like in the history across different iterations, how did your parameters evolve, and so on, right? So this is literally as simple as running a complicated QAOA problem. All it requires is a bunch of steps. Perfect. So
Vishal, I think we already spent 2 more minutes.
Okay, I'll just literally take 2 more minutes. I promise this is the last slide I want to talk about.
Okay.
So at the moment, if you go to GitHub now, you can't access OpenQAOA because it's a private repository. And that's because starting May 2022, we were working on this closed beta, where we had the private access to the closed collaborators, and they basically interact with the repository and they tell us their feedback and so on. But starting July, we plan to go open source with it. Well, it could be July, late July, or let's say mid of July, depending on how the consolidation phase goes. But essentially, the idea is to take some of the feedback from these private collaborators and essentially finish up a few last touch details that we want to before we finally open source OpenQAOA and GitHub. So it goes without saying, like our goal is basically to expand this project into an open source community-driven project. And that's essentially one of the reasons we're going open source with it. And we would absolutely love for you to participate. Like if you think this is something interesting for you, and if you think this is something actually useful for you in what you do, then we would be really happy, and feel free to reach out to us. And if you still think that you're too excited about this project and you absolutely do not want to wait until July, then again, feel free to reach out and maybe we can already give you access for the closed beta as well. With that, I conclude my presentation for today. And if we have some time, we can go through the questions.
No, sorry, we don't have time. Thanks, Vishal. All questions should go to Discord. Thank you very much.
Okay, then I'll head over to Discord and I'll tackle those questions. Thank you.